Alright, my name is Zachary Zimmer, and I'll be the group leader for the refrigeration cycle. First, a little overview of what we do. I'll give you an introduction of what the refrigeration cycle is. Then I'll give you an overview of our apparatus, of how it will be being used. Next, I'll show you the diagrams that we use to read charts to solve problems for the refrigeration cycle. Next, I'll talk about the ideal and actual cycles and the differences between them. And then we're going to do a sample problem with a solution. The introduction of this: in this experiment, we want to analyze the performance of a refrigerator, which is necessarily like the heat pump. We want to take the coefficient of performance of it. That's what we'll be looking at. But what a refrigerator does is basically it can cool a hot room, or it can heat up a cold room, whatever one you prefer. We're looking at the refrigeration cycle, which would be more of cooling of a hotter room. You mainly can get this from looking at the pH diagram, which is the pressure versus enthalpy. Our main apparatus that we have here, as you can see, we have our condenser, an evaporator. We have two water pumps that were the blue things at the bottom, and a compressor. The fluid we'll be using will be R134A. And the main functions that we want to get from this are compression, condensation, evaporation, and expansion. As you can see in the middle, there is an expansion valve, which I'll go more in detail about that later. Our first diagram we have here is our pressure versus volume. It just shows what the working fluid will be going through. We'll start before the compressor, and the compressor is going to raise the pressure of it and slightly decrease the volume, just because like we're compressing it. The air is going to hit the condenser, where it will turn all gas into basically try to get it all into a liquid. When it's at its liquid stage, it will then go and be throttled to an evaporator, and it will just keep repeating this process. Here you can see is a TS diagram, the temperature versus our entropy. You can see the apparatus to the left as well. You can see where states are 1, 2, 3, and 4. The expansion valve is in between 3 and 4 again. As I said, I'll talk more about that later. The dotted line from 3 to 4 represents an ideal case of where it is like perfectly reversible, and you can have basically no friction is within the cycle. It's an easier way to do calculations to perform for efficiency. But as you can see from 1 to 2, it's the isentropic compression. Then from 2 to 3, constant pressure. 3 to 4, throttling and expansion valve. The ideal case is where the entropy would remain the same. Real world scenarios, this doesn't happen, as you see in the next graph. This is the actual like real world. If you have to deal with friction and everything, what will actually happen. It actually go to 1 to 2, and when it's going through the compressor, as you can see through here, some of it will be compressed, but also some will go straight through. That's why we have this line right here to go straight across. The dotted lines, again, are going to represent an ideal case. As you can see, there's many more points in here due to friction and more bends and stuff in valves. You're going to have more losses. Now on to expansion valve. What the expansion valve does, in between 3 to 4, as you've seen on all of the diagrams, it only controls the flow of liquid into the evaporator. It does this by dealing with pressure. The expansion valve removes the pressure from the liquid refrigerant to allow for the expansion for the refrigerant to be evaporated when it gets to the evaporator. Alright, and as you can see here is our pH diagram, which is used. This is the main component we use to solve for our problems. When you're reading this, this is a visual representation of an ideal case. As you can see, from 3 to 4, our entropy, or enthalpy, is staying the same. And over here you can see some formulas on how it correlates to the first law. And through the components, what processes will stay the same. Like in the compressor, we'll have constant entropy. Through the condenser, our pressure will stay the same. And on the right is just our formulas we use. And our coefficients of performance is basically our efficiency. And to do this, it is our heat that's lost over our work that we put in. is how we do our coefficient of performance. This can also be written as, you can find it with this enthalpies from the chart used. To go on, we have a sample problem of this. As you can see, it's using the same refrigerant as we are. Pulled this out of a textbook. This isn't any values correlated to what we're doing, it's just to give y'all a good understanding of how everything's gonna work. So as you can see, it has the things you need at each state on the left. It has the values that you can find in the charts from the back of the book. And on the right is plugging them into the formula to find for the coefficient of performance. And as you can see, for this problem, they get a final answer of 3.41. And that is all for my presentation. Do you have any questions?